Hey all, let's do another problem. So this problem was from CS 109, and it was a pretty hard midterm problem. I thought it was a really cool problem because it is analyzing a greedy algorithm. And in this class, you will definitely analyze a lot of greedy algorithms. So let's try to work through this problem. A class has K students and R sections. Each section can have M students max. They can have less, even 0. Each person gives exactly one preference, and the student's preference is equally likely to be any of the R sections. The greedy algorithm then goes through the students in some arbitrary order. When you consider a student, you check if there is space in their preferred section. If so, you assign them to this section. Otherwise, they're unassigned. So just as an example, let's say your students, so student 1, that's 0 index, so student 0, student 1, student 2, student 3. And let's say, so this is K equals 6. Let's say there are 2 sections, one led by me, and then one led by my roommate, Jose. He's also a 161 TA. He's a great teacher. I recommend this section. But let's say you had a choice between me and Jose. And obviously everyone's going to choose me. Well, everyone except S0, but no one likes S0. But everyone else is going to choose me. And then, so we have 2 sections, 6 students, and each class, let's say they can have at most 3 students. Then what's going to happen is we will go through the students in some order, and then we're going to assign the student to the section if there's space. Assign S0, assign S1, S2, S3, S4. But then when we try to assign S5, there's no space in Avery's section, so they're just left unassigned. Right? And the problem we want to answer is, what's the probability that the very last person considered by the algorithm is unassigned? So what we should remember here is that each student's preference is random. It's equally likely to be any of the sections here. All right, so let's try to consider what needs to happen for the last student to be unassigned. For the last student to be unassigned, we need there to be, out of the first couple, like out of everyone before them. So let's say the last student was K minus 1. This is the last student. So there are K minus 1 students in front of them. So K minus 1 students. And we need SK minus 1 to not be able to join the section that they want, which means out of all these K minus 1 students, there needs to be at least M students who want the same section that SK minus 1 wants. All right, so at least M students who want the same section. That's a little, hard to calculate. We have to calculate this at least part. So let's just consider what is the probability that exactly, let's use some other variable, J, students want same section that S sub K minus 1 wants. Well, that is equal to, so we need the students in the front. We need all those students in the front. We need exactly J of them to want the same section that S sub K minus 1 wants. And we want the other, the other K minus 1 minus J students to not want that section, right? We need exactly J students who want that section, not any more, not any less. Right? Now you should recognize that this is a random variable, right? I guess we can say that the number of students that want the number of students that want the exact same section that S sub K minus 1 wants, let's get that a random variable. And you should recognize this random variable is a binomial. Right? Because each student in the front has some probability that they will want the same section that S sub K minus 1 wants. What's that probability? It's 1 over R. right? Because there are sections, each one is equally likely. So every student is has a probability of 1 over R to choose the same section that S of k minus 1 wants. And then there are how many each trial is independent because each student chooses their preferences randomly. So there are n students, and then the probability of success of the fact that you want that student ends up in the same section as S of k minus 1, that's 1 over R. And we want to calculate what the probability that X is equal to J is. Or rather, we can simply just solve the problem immediately. We want the probability that X is greater than or equal to M. So that's equal to the sum of J equals M all the way up to the maximum possible value that X takes on, which is N, of the probability that X is equal to J. And now, what is the density of a binomial? Right, if you don't remember, don't worry, but you should sort of remember this, write it down in your notes. It is n choose J times the probability of success. Here it's 1 over R to the jth power times probability of failure, 1 minus J R raised to the n minus J power. Right. So here is number of ways, or rather here is the probability that the J students want SK minus 1 section. Here is all other students don't want that section. Right, we need both to happen. But then there are a lot of different ways this could happen, right? Because this focuses on a particular set of students who want that section. But in reality, like we could choose any of the J section. We can choose any of the J students to want that section. So this is to account for possible ways to pick the students who want the section. All right. Yeah, if you don't quite remember this, go review CS 109's section on binomial probabilities, binomial random variables. You'll see this happen quite a bit in CS 161, I'd say. All right. And this is the answer. We have our answer. All right. What else? All right, it seems like I think I'm missing something here. Oh, yeah, I see what I'm missing. This should be n minus 1 because there are n students, but we only care about what the first n minus 1 students want, right? And then we want to try to match them to see if they get the same section that S of k minus 1 is. So this should be, this is R, and then the number of trials, n, is actually equal to k minus 1. So every time we have an n here, we should be replacing that with k minus 1. K minus 1, k minus 1. And k minus j minus 1. All right, there's the final answer. All right, don't forget to plug in the variables of the question. All right, now let's do part B. Part B is asking, what is the expected number of people who will be unassigned? So now it's not just the last person, but we want to calculate what the probability that any of the other people are unassigned. So let's actually calculate. What's the probability that person I is unassigned? And we can sort of generalize the answer we have over here, right? If we're not dealing with the last person, we're dealing with someone before the last person, well, we still have the same calculation we have over here. But instead of, the only thing that changes is the number of students in front of them that we have to calculate, right? So here, we were worried that we had to worry about the first k minus 1 students. But if you're only considering the ith student, then how many students are before them? I minus 1 students. So the only thing we have to change to calculate the probability that the person I is unassigned is, instead of k minus 1, you'd replace that with I minus 1. So this is equal to I minus 1, k minus 1 choose j. So this should be I minus 1 choose j, 1 over r to the jth power, and 1 minus 1 over r to the I minus j minus 1 power. So then what is the expected number of students unassigned? That's equal to the sum of, so we have to consider what's the probability that each student is unassigned. So I equals 1 through k minus 1 students. Actually, we would have to do this until k, right? Because we have to consider the last student, the k student as well. Of m of 1 of, and then we can just plug in the probability that person I is unassigned. So that would just be sum of I equals 1 to k, sum of j equals m I minus 1 of I minus 1 j, 1 over r to the jth power, 1 minus 1 over r to the I minus j minus 1. All right, there's one last thing we have to deal with, and that is this summation, right? Think about it. Can the first person ever be unassigned? No, right? Because the first person will always get the spot. And in fact, the first r minus 1 students, r minus 1? No, r is the number of sections. The number of m actually. So the first m minus 1 students should always get a section. It is the mth student. So if we're zero indexing, the mth student might not get their section. Like the mth student might not get their section if everyone before that person wanted the same section that the mth student wanted. So we don't actually have to start the summation at 1. We can start it at m. And that is our final answer. All right, thanks for watching. See you in the next video.